Forgive me for doing a little reading here, but I really want to reorient what this is all about. It's possible to transform every value in a distribution into a corresponding z-score. And of course, there'll be fractions sometimes, decimals. The result of this process is that the entire distribution of values is transformed into a distribution of z-scores that balances out with negatives on the left and positives on the right. The distribution of z-scores have characteristics that make the z-score transformation a useful tool. If everything is transformed into a z-score, then the distribution of z-scores will have the following properties. The shape will have the exact same shape as the original distribution. Now let me say this, we're only concentrating on normal distributions, but we could be looking at skews. Quite reasonably, we don't look at skews on these graphs. That would just be too much to get into, but we could. And transforming raw scores into z-scores does not change anyone's position in the distribution. For example, any raw score that's above the mean by one standard deviation will be transformed to a z-score of +1, which is still above the mean by one standard deviation. Or if it was 2.5 standard deviations below, it'll be transformed into a z-score of -2.5, etc. So because each score stays in its same position within the distribution, the shape doesn't change. The mean, the z-score will always have a mean of 0, that z-score distribution, because the mean is 0 standard deviations from the mean, if that makes sense. So in that figure 5.6 that we saw before, the original distribution of x values has a mean of mu equals 100. But when this value, x equals 100, is transformed into a z-score, the result, of course, is 0. And you can see the plain math there. So the original population mean is transformed into a value of 0 in the z-score distribution. And, of course, each number that's a standard deviation or below is transformed into those individual numbers. And one other property, the distribution of z-scores will always have a standard deviation of 1. And I would reference you to 5.6. The original distribution of x values has a mu of 100 and a standard deviation of 10. When we transform it, it's going to be a value of 110 will be exactly 10 points or one standard deviation above. So fairly direct idea. So here we have a notion, and this is figure 5.6 that they've been referring to. And of course, you can always reference your text. An entire population of scores is transformed into z-scores. The transformation doesn't change the shape of the distribution, but the mean is transformed into a value of 0, and the standard deviation is transformed to a value of 1. So, and then of course a value could be 1 or 2 standard deviations, etc. So what's the value of all this? Why would we undergo these mechanics? Well, as we can see again, a standardized distribution composed of scores that have been transformed to make it easy. So I've got this easy to relate graph here. It's just really quite cakey. I've transformed everything into z-scores, and of course, as we've talked about, the sum of the scores will always equal 0. But I can make comparisons. Walk with me on this example. One advantage of standardizing distributions is that I can make it possible to compare different scores on different individuals. So, for example, the student received a score of 60 on a psych exam and a score of 56 on biology. For which course should this student expect the better grade? Well, that's interesting. I don't know. I'd have to have some, basis for comparison. Well, let's take a look. Instead of drawing the two distributions to determine where Dave's scores are located, we can simply compute the two z-scores to find locations. For psychology, Dave's z-score is 60 minus the apparent mean of 50, and the standard deviation was 10. Okay, so he was exactly one standard deviation above the mean on that particular test. We were just now told that the standard deviation was 10, and indeed his score was 60. So he's got a z of +1. For biology, Dave's z-score was 56 minus 48. He was 12 above. Am I right? 8 above. Math is hard. Everything's fine. And the standard deviation was 4. Now, we didn't know that, but nonetheless, that's what it is. So in his case, he is 2 standard deviations above the mean. Well, I'd like to hear that. So in that case, we'll say, well, great. It looks like Dave's biology test score was more impressive. So there are countless things that wouldn't necessarily be comparable if we didn't know these parameters. Like if I said, hey, your resting heart rate is 70 and your blood pressure is whatever the heck it is, maybe 130 over 90, I don't quite know what to make of that. Maybe 70 is actually one standard deviation below the mean, and 130 over 70, and I'm making these numbers up, is a half a standard deviation below the mean, something like that. Well, in that case, I would say the heart rate is more impressive. It's suggestive of an efficient system. So if I'm coming into something, here's another thing. Imagine if you were gauging high or college admittance based on high school statistics. Tell me about this incoming student. Well, a student has an ACT score that's very high, 30. What do I know about 30? 30 is 2 standard deviations above the mean. Oh, how about them apples? Tell me about their GPA. Their GPA was 3.8, and to tell you the truth, that's only 1 standard deviation above the mean. So I could say, well, geez, their GPA was pretty good at 1 standard deviation above the mean, but the ACT score was even more impressive at 2 standard deviations above the mean. And if I knew the parameters, the means and the standard deviations, I could compute that, although the raw numbers themselves don't necessarily tell you that.